It turns out that at these very low atomic numbers, see it says number of protons, so that's the low atomic numbers, that the stable ones that are here in this kind of a teal color run right along this line. Well, what is this line? Well, here's 100. I go up to 100 on the line, and it's 100 here. Oh, this is number of neutrons. Okay, so this is the line where it's a 1-to-1 ratio, and at these very low atomic numbers, in other words, if you look at it, this looks like through the end of period 3, not including transition metals, it looks very much like it wants to have a 1-to-1 ratio. This is called the belt of stability, and it gradually requires more and more neutrons to keep something stable. Because those, let's think about what those nuclei look like. They've got a whole bunch of positive charges that all hate each other and want to fly apart. But the neutrons are there kind of keeping things calm. But the more of them you pack in there together, the more you need the neutrons to keep things calm. Eventually, there's nothing, it won't work at all. You end up with the last of our periodic table being full of nothing but radioactive particles. All the elements are radioactive after a certain point. So the ones that are stable are the ones that are the teal. The ones that are unstable are what we call the radioactive ones. We have the belt of stability, and at low numbers, there's that 1-to-1 ratio between neutrons and protons. And then it goes up and up and up, all the way up to 1.5 to 1 before you're all done with it. As you can see, here is 80. We go up when we hit 120 to get something that is stable. And then we can tell whether a particular nuclei is neutron rich, that would be above the teal, or neutron poor, that would be below the teal. And radioactive decay is a spontaneous process, and we say it's accompanied by the release of radiation. We have 4 types of decay. Alpha, beta, those are the two that were discovered first. They got these names, and they're alpha, beta. Gamma is another type of thing that you will hear about as far as the radiation that occurs. But these were named earliest. They got nice Greek letters given to them. Positron emission and electron capture. And which type you're going to end up having happen is influenced by whether you're neutron rich above the belt of stability or neutron poor below the belt of stability. Here we have a nice little table that tells us what the symbols are for some of these subatomic particles, all right? If we have a neutron, it has no charge, so there's a 0, but it does have a mass of 1, what is considered to be 1 atomic mass unit, which turns out to be a very small number if you express it in kilograms. A proton could be written either as a P for proton, it's got a charge of +1 and a weight of 1, or you could write it as, hey, that's a naked hydrogen, right? It doesn't have an electron with it, so it has a positive charge and it has a mass of 1. The electron could be written as the beta particle, or you can say, yes, E for electron. But in either case, it's got a charge of -1 and a mass of 0. Is it really a mass of 0? No, here's the mass, but you can see it's 1,000 times less than the masses of neutrons and protons. So we just say, close enough. We're going to call it 0 for a mass. A deuteron, hydrogen itself has isotopes. And the most common isotope is that instead of having no neutrons, it will have 1 neutron. So if you have 1 proton and 1 neutron, you're going to have a mass of 2. And so if you look at this, it ends up, and you'll see they actually use D for deuteron, because that would tell you that it's second, 2. All right? That's what's going on with that name. Or, of course, you could just say it's a hydrogen that happens to have a neutron in there also, so its mass is twice instead of just the 1. The alpha particle is, you can write it as alpha, or it's a naked helium. So helium is element number 2, so 2 protons. But whenever you have helium, the stable form of it has 2 neutrons also, and so you end up with a mass of 4. And then there is the positron. When you have the positron, it's like an electron, but it's the opposite charge. So you see they will write a beta for it. It'll have no mass, but instead of a -1, it'll have a +1 charge. So it has the positive charge like a proton, but it has the mass like an electron. And that's your positron.